Number 10, phosphate buffer. So in number 10, it's just twist the question, but basically it's just ask how to prepare the phosphate buffer. So for 10A, you have either phosphoric acid, H3PO4, and hydrochloric acid, and sodium hydroxide, and you have to make the buffer at pH 7.21, right? So, okay, so first you have to determine the amount of the amount of phosphoric acid that you're going to put in the beaker. And since we know that phosphoric acid is basically like very acidic form of the H3PO4 is a very acidic form of the phosphoric acid. It's starting from the left side of the equation and going to the right side. So starting from the acidic side. So to raise the pH to 7.21, basically you need the base to do that. So for these questions, you need to calculate the amount of H3PO4 and the amount of sodium hydroxide because you need base, right? And then calculate the amount of water that you need to top up to reach 500 mils. So to calculate the amount of H3PO4 that you're going to use, we're starting from looking at the moles of what we want. So we want our buffer to be 0.5 liters. The concentration is 50 millimolar. So the moles of the phosphate ion that we need will be equal to 0.5 liters times by 50 millimolar, and this equal 25 millimoles. So from the equations, we have 1 molar of H3PO4. So to calculate the volume of H3PO4, so again, I know that you, have done this many times, so you need to use the moles and then divide by the concentration. And you get 25 milliliters. So the H3PO4 that we're going to put in the beaker is 25 milliliters. Next, we need to determine the amount of base that we need to raise the pH. So to calculate the amount of base that you're going to use to raise the pH, you have to again look at how phosphoric acid deprotonations. So yeah, and look at the pKa. So we starting from H3PO4, and since we doesn't know the pH of H3PO4, we assume that it's very, very, very acidic, right? And we need to raise the pH to 7.6 here. So the step that that you need to work here is that first you have to change H3PO4 to H2PO4 minus, right? And then change it further to HPO4 2 minus. So again, it's the same as the homework from the first midterm. So right now you should be able to understand the approach of these questions and how we calculate for the amount of the base equivalence that we need to raise the pH here. So I would not completely explain everything, and you should go back and review the homework from the first midterm. Sorry, I made some mistake here. So it's not 7.6, that is the second part. Okay, so make the offer at pH 7.21 actually. Okay, so for the step 1, we know that from the chart here, we know that we need one equivalence, one equivalence to change H3PO4 into H2PO4 minus. And then for step 2, you have to use the Henderson-Hasselbalch equation to calculate the B ratio, right? And if you notice that the pH that we want, 7.21 here, is actually equal to the pKa, correct? So you basically don't need Henderson-Hasselbalch equation, because we know that if the pH equals pKa, it means that at that state, you would have the A and B ratio equal 1. So you would have 0.5 equivalence that is in acid form, and would have 0.5 equivalence of basic form in that state. So we know that the step 2 here, you focus on the B ratio, you need to add the base for 0.5 equivalence. So the total of hydroxide equivalents equal 1 plus 0.5. So you need 1.5 equivalents of the base to raise the pH to 7.21. So moles of hydroxide ion using the equivalence times by the moles of the phosphate buffer, which is 25 millimoles, right? You get 37.5 millimoles of the base. So to calculate the volume of sodium hydroxide that you need, again, using the moles and divide by the concentration of the NaOH, 10 molar, right? So you get 3.75 milliliters. In summary, you have to pipette H3PO4 25 milliliters, pipette sodium hydroxide 3.75 milliliters, and then top up with water to reach 500 mils. Okay,